had not yet time to. I had not yet time to put the videos in YouTube. I noticed that there was some. I would not use the word. Some guy placing. I think it's a pornographic site link in the comments. So I had to clean these comments, to block these comments, so that now they are not appearing. But I noticed that this was happening concerning this course here. So be careful. Don't if you see links on the comments, don't click on this link on these comments. Okay, when you go to YouTube, there are comments. If there are comments, at this moment there are not, but if there are comments, and if you see some link, don't click. I'm saying this not because that I'm afraid that you will be shocked, but because there can be something that can harm your computers. Okay.
Thank you.
Thank you.
So, and it took me some time. I was updating the file with the links, but then I found this problem, and I was checking all my videos. It was apparently on the last two sessions that there was some. Apparently not the same person, but it was the same person. You see, these criminals, they come from who knows, God knows why, where, no. Okay, so we were speaking about the homogeneous equation. And the homogeneous equation is x dot equal to ax. And I have some initial condition. And then I said, okay, the solution gives some, you have the solutions in time. So you eliminate time and you have a line in state space. In this case, I have two state variables. So the state space is just a plane. And I start with the initial condition and I go on integrating the equation, and I have a curve that I call an orbit or a state trajectory. It's just the solution, okay, x2 as a function of x1. And I said, oh, okay, now I can consider different initial conditions, and I can have many orbits. And the set of all the possible orbits is the phase portrait. And the phase portrait, at each point x, each trajectory is tangent to ax. And then I said, okay, now I would like, instead of integrating the equations, I would like to compute eigenvalues and eigenvectors of matrix A, and to find out what is, at least qualitatively, the type of phase portrait that I have. So we went on to the discussion of what are the eigenvalues and the eigenvectors of matrices. And I said that the definition is, if I have an eigenvector of a matrix A is a vector such that if I multiply the matrix by the vector, I get another vector which is proportional to the original vector. So the direction of the vector is not modified, although the vector can be stretched or compressed according to a scale factor, which is the eigenvalue. So the eigenvectors do not change. If you think of multiplying by a matrix as a geometrical change of the vector, the eigenvectors do not change direction. They only change the length. And the scale is lambda I. Okay? How can I compute them? I use the definition. So this equation is equivalent to this one, and this is a matrix times Vi equal to 0. Then we said, okay, this matrix must not be invertible, otherwise the only solution is Vi equal to 0. And for this matrix not to be invertible, we have to impose that its determinant is 0. So we get the lambda I from this equation, and then we go back to this other equation, set of equations, and solve it. Okay, so this is a polynomial equation that gives you the lambda I. Then I plug it here and I solve this. And since the determinant of this matrix is 0, then the equations are linearly dependent. There is a dependency. So one equation can be obtained from the others. So you have more unknowns than the equations, and for that you have to impose something on the V. And I said, well, impose the first component, or impose the lengths, okay, or any other thing. But you have to make impose some other characteristic or some other feature of Vi. And we did an example. So we did this example, finding the eigenvalues and the eigenvectors of this matrix. And so I build A minus lambda I. Then I compute the determinant of this matrix and equate it to 0. I get a polynomial equation. And the roots are -1 and 2. So the eigenvalues are -1 and 2. And now the matrix A minus lambda I Vi is this one for lambda 1 equal to -1. So I plug here lambda for lambda 1, and I get a set of equations. Okay. Now this is 5 V11 minus 5 V12 equal to 0. And 2 V11 minus 2 V12 equal to 0. So the second equation is obtained by from the first one by multiplying by 5 and from multiplying by 2 and dividing by 5. So they are really not different equations, but they are equivalent equations. So what you have to do is you impose one of the components, say the first one, and then solve for the other, and you get 1, 1. And also here, for lambda 2 is the same. So the eigenvalue corresponding, the eigenvector corresponding to lambda 1 equal to -1 is 1, 1. And the eigenvector corresponding to lambda 2 equal to 2 is 5, 2. Or if you want, 1, 2 divided by 5. Okay? Which is 0.4. 2 divided by 5 is 0.4. So if I have here 1, I have here 2 divided by 5, which is 0.4. That's the number that we got with MATLAB by dividing the first one by the second, or by dividing the second by the first. Okay. Any question about eigenvalues and eigenvectors?
No.
Okay, so let's now do something which is really interesting. Up to now, this is a definition. Suppose that we have a matrix with n linearly independent eigenvectors. This does not always happen. For instance, Cave was picking up an example in which this was not true. However, if you write a matrix at random, probably it will have n independent eigenvectors. Okay, so the number of matrices with n independent eigenvectors it's an infinite number, but it's an infinite of order bigger than the ones that they don't have infinite n independent eigenvectors. Okay. Anyway, my concern is just to simplify things. I can tell you, if you pick up a matrix later, if you pick up a matrix without any independent eigenvectors, then all the conclusions that we are going to take will change. Later we will discuss that. So assume that A has n independent eigenvectors. Okay? And form a matrix that I call M. It's the modal matrix from mode, the way in which you behave, which is made of placing the eigenvectors as columns. Okay, so you have n independent eigenvectors, you place them as columns. You have n columns here. So this is n by n matrix. Is it invertible or not? Can you say something about invertibility of M? No ideas? If all the columns or the rows, that's equivalent, of a matrix are linearly independent vectors, then the matrix is invertible and the determinant is not zero. There are three things that are equivalent. Okay? So saying that the matrix is invertible, or that it has n independent columns, or that it has n independent rows, or that the determinant is zero, they are equivalent things. Okay, so this matrix is invertible. And I also place the lambdas in a diagonal matrix. So lambda is a matrix of zeros, but in the diagonal we have lambda 1, lambda 2, lambda n, and then so on. Okay? Any question? Now, we have the definition of eigenvector. Okay? And from this definition, if you think that you have, instead of multiplying A by Vi, you multiply it by A, by V1, by V2, by V3. So you multiply A by M. Okay? You multiply the rows of A by each of the columns of M. Each of the columns is the Vi. So you get the lambda I, Vi, and it looks like it would be lambda M, but no, it's M lambda. So if you do an example, a 2x2 example, you can convince yourselves of this. Now, since the inverse of M exists, I can multiply on the right by M minus 1, by the inverse of M. So A, M minus 1, M minus 1 is the identity. So A is equal to M lambda M minus 1, which is here. Okay? So if a matrix has n, the length of the side of the matrix, no, as n independent eigenvectors, you can write the matrix as the product of the matrix formed with the eigenvectors times the matrix, which is the diagonal of the eigenvalues, times the inverse of the matrix of the eigenvectors that exists because, as I mentioned to you, if a matrix has n independent independent columns, the inverse exists. Okay? So you can write your matrix in this way. Or you can look the other way around. So pick up this formula and you multiply on the left by m minus 1. So you have m minus 1 am equals to m minus 1m, which is the identity lambda. So m minus 1 am equal to lambda, and you get the second formula. So if you pick up a matrix A you multiply on the right by the matrix of the by the modal matrix of the eigenvectors. And on the right by its inverse, you get a diagonal matrix, and this diagonal matrix is the matrix of the eigenvalues. Okay? This is provided that we have n independent eigenvectors. If we don't have n independent eigenvectors, this is not true. Okay? Any question?
No.
So let's now use these formulas. Okay. Okay, now suppose, let me make you an historical question. About 2,000 years ago, who were the guys running Portugal?
In the house?
Yeah?
In
2,000 years, who were the guys who were in Portugal?
Who were the guys running Portugal 2,000 years ago?
The Romans?
The Romans, okay? This was part of the Roman Empire. So you can imagine Roman kids at school, and they have to multiply things, numbers. Okay, so the teacher asked a Roman kid to say multiply 35 by 57. Multiply. Okay? You can imagine that the poor Roman kids were always receiving, being beaten according to the pedagogical methods of the time. But now imagine that an Arab kid came to do Erasmus in Portugal. Erasmus was not even born at the time, but let's figure out. And yeah, the Arab kid said, okay, now I have a better representation for the numbers. So instead of representing the numbers like this, I say 35 by 57. Okay? And I want to multiply. So this x now means multiply. So I only know this in Portuguese. 7 vezes 5, 35 e vão 3. 7 vezes 3, 21 e 3, 24. 5 vezes 5, 25 e vão 2. 5 vezes 3, 15 e 2, 17. 5, 9, 9, 1. Okay, so the answer is this one. But you have to express it in Roman numbers. So
M?
Yes?
It's an M? No?
It's what? In Roman numbers?
I'm telling you, it starts with the M.
M, 1,000.
Then is a C.
Then
A
D,
C.
for 500. And then a C, 600, 700, 800. So actually, it's more complicated because
can it be a C before a M to make the 900?
That's right. That's right. You're much better than me.
So MCM.
I see that you are an expert. MCM.
No, my wife. No, I'm not an expert. My wife had a lot of Latin in university, so I remember a lot.
And now XC 90 and then 5. Okay?
Yeah.
So what was really impossible to do with this representation, okay, So from going to here to here, from here to here, it would have been impossible. But now you do this turnaround. You do this turnaround, okay? So you do a change of coordinates, a change of representation. And then you do the inverse of the transformation. Okay? By doing this, with this change of representation, you transform your problem into a much easier problem that you solve, and then you use the inverse of the transformation that you have applied to get the answer. Okay? This is a very powerful way of thinking. Just give me a moment because my TV started making noises. Okay, so let's go back. Let's go back to our problem, or to let's go back to our homogeneous equation, and I want to solve it. Okay, I want to solve it, and I'm going to apply this idea. So what I'm going to do is I'm going to change the state and define the new state Z, which is the inverse of M. M, remember, is the matrix whose columns are the eigenvectors of A. So M inverse multiplying X, or if you want, X is equal to MZ. Okay? Now, I want to get an equation for Z. And for that, I differentiate this definition of Z. So Z dot is the derivative with respect to time of M minus 1X. Now, the derivative, I can interchange it with a multiplication by a constant matrix. So the derivative of M minus 1X is M minus 1 times the derivative of X. Okay? And now for X dot, what can I use? What
is the what?
What?
The homogeneous,
That's right. So
equation.
X dot is what? Is AX. Okay? But I want an equation for Z, and this still uses X. So what shall I use?
The one above X equals to MZ.
That's right. So you end up with Z dot equals to M minus 1 AMZ. But M minus 1 AM, it's a matrix. And we have shown that this is lambda. This is the diagonal of the eigenvalues. Okay? Now, let's go back to the whiteboard. And let's clear everything. So I came to the conclusion that Z dot is equal to lambda Z. So suppose that Z has just two components, Z1 and Z2. Okay? So Z1 dot, Z dot is Z1 dot, Z2 dot. this is lambda, lambda 1, lambda 2, 0, and 0. Z1 and Z2. Okay? You agree?
Yes.
Okay.
Now I multiply this matrix and I get that Z1. Z1 dot is lambda 1 Z1 plus 0 Z2. So this is just lambda 1 Z1. And the other is lambda 2 is Z2 dot equals to lambda 2 Z2. That is to say, by doing this change of coordinates, I decoupled the equations. Okay, so in X, the equations are coupled. X1 depends on X2, and X2 depends on X3, that depends on X1, and so on. But in the Z coordinates, Z1 only depends on Z1, Z2 only on Z2. Okay, and this was obtained by rotating and perhaps stretching your coordinate systems. Okay, now what is the solution of this equation? So Z1 of t is what? So what is a function that if you differentiate it, you get lambda 1 Z1?
Exponential of lambda 1t.
Exponential of lambda 1 t of lambda 1 t, okay, multiplied by t. And you put here times some constant that I say, which is Z1 of 0, no? Because otherwise it would start in 1. And I want it to start in Z1, 0, no? In Z1. That can be anything. So for t equal to 0, this is exponential of lambda 1, 0 is 1. So it's a constant times exponential of lambda 1 t. And the same for the other, no? Z2 of 0, a constant, lambda 2. If you want, instead of writing these things like this, you just put here K1 and you here K2, so some constants, okay? But now, you don't want the solution in Z, you want the solution in X, okay? So, if you want the solution in X, if you want the solution in X, okay, so we have these solutions in Z. Now, if you want the solution in X, you know that X is mz, so you multiply this matrix by this vector, and you get this wonderful formula. So X is a sum of terms made of what? A constant. Then you have an eigenvector and the exponential of an eigenvalue times time. Okay? So each of these terms is called a mode. Each of these terms is called a mode. So you are saying that your system, the solution of your homogeneous equation is a sum of modes. A solução da equação homogênea é uma soma de modos. And each mode depends on the eigenvector and the exponential of the eigenvalue times t. And then these constants depend on initial conditions. Okay? These constants depend on initial conditions. Suppose, for instance, that you have a dish of soup. Okay, maybe you have, when you are at home, you have to carry a dish of soup from the kitchen to the dining room. And you see that the soup is oscillating. Okay, that's one mode of oscillation of the soup. Okay, so now you can do another experiment. Shake the little bit the dish and shake with enough velocity. So instead of having the soup making like this, it ondulates a little bit. So that's another mode of oscillation corresponding to a faster eigenvalue. And if you shake it even more, you know what happens? In the case of José, are you married, José Basílio and Cave?
No, I'm not married.
You're not married. What about you, José?
I'm not married, but I consider that I'm married.
Okay, so
There's no difference.
your girlfriend,
Yes.
the result is that your girlfriend will pick up some dish of soup and will throw it for your head if you start shaking it over the carpet. That's the result. Okay,
Yes,
so
over
the
the
idea
carpet, yes.
is that you have different modes. You can do the experiment. Also, you, Cave, I mean, go to your parents' house or to someone that is a friend of yours to pick up and say, I'm going to help you bringing the soup from the kitchen to the dining room. Now I'm going to make an experiment that I learned with Professor Miranda Lemos in the, okay, you want to see, it's a scientific experiment. And you see different modes of oscillation. Always a vector times the exponential of an eigenvalue. But what is really important here is this eigenvalue y. Why? Can you tell me why? For instance, the eigenvalues are complex numbers. Okay. Suppose that you have just two. It's a second order system. Okay, it's a second order system, and so you have two eigenvalues, and they are, both of the eigenvalues are real and negative. -1 and -2, for instance. Okay. So what are these exponentials? What happens to these exponentials when time passes?
They go to zero.
They go to zero. So the system is stable, asymptotically stable. Okay. And can you find some oscillations in this case?
Oh, shoot.
The exponential is, since you have two different exponentials, perhaps it goes up a little bit, but then it goes down. It never oscillates. Okay. So if you have negative eigenvalues, you will have an asymptotically stable system. The transient dies out, and you don't have any oscillation. Now, suppose that one of the eigenvalues is positive. They are real, and one is positive. What happens? What happens to x?
It will go to infinity.
You have a positive exponential, so it goes to, now depends on the corresponding value of k. Okay, but in general, if the k that multiplies the exponential with a positive eigenvalue go to infinity. Okay, so you have an unstable system. Again, no oscillations. Okay. Now, suppose let's go to the whiteboard. Suppose now that you have lambda, say lambda 1, which is -2 plus j. J is the square root of -1. Okay? What do you usually call the square root of -1? What is the letter that you use usually?
I.
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 I'm an electrical engineer, so I use I for current. Okay, so the electrical engineers use J for square root of -1. Okay, you want to call it I? Let's call it J. Let's call it J.
Doesn't matter what is it, as long as we know.
Okay, so our xt is k1 v1. Remember that this is a vector exponential of -2 plus j, sorry, multiplies time plus k2 v2, and then what should this other eigenvalue be? It should be complex conjugate, because x is real, so these two numbers must be complex conjugates. You know what is the complex? If you have a plus jb, what is the complex conjugate of this number? So you have a number,
JB.
v, let's call it v, and the complex conjugate, I put a star. That's the complex conjugate of v. That is what?
A minus GB.
A minus jb. So the fact is that if you sum both of a number which is conjugate, what you have?
2 times the real part. 2A.
Okay, so 2 times the real part. So it's a real number. Okay, so this term must be conjugate from this one, and this means that this eigenvalue must be conjugate from the other one. So I have -2 minus j t. Okay, so such that in the end xt is real, is a real number. Now let's look at this term here. We have, this is the exponential of the sum, so this I can write this as -2t exponential of jt. Okay, you understand why? Because
we stay with the base and we sum the exponentials.
That's right. That's right. Okay. Now, so this is equal to that, and this is exponential of -2t, and the exponential of jt. You know, it's Euler's formula. It will be cosine of t plus j sine of t. Okay, so the exponential of a pure imaginary number is a cosine and a sine. The j will cancel out because you have the other term. That's the idea. Now, this term, what does it give? What is the shape of this, of, say, for instance, the exponential of -2t cosine of t? What is the shape? What do I get? So if I do a plot, I have t, and here I have e minus 2t, cosine of t. What do I start here, and what shall I do?
Go down
And
then
then
oscillate.
oscillate, and the amplitude of the oscillation, what happens to it?
Decreases.
Decreases. So I have, you may admire my capacities of drawing. Is it beautiful? Remember that in the end I will give you the grade. So is it beautiful?
Yes.
Yeah,
Yes.
sure. It's wonderful. You should say wonderful. Okay.
It serves this purpose. We understand what it means.
Okay, that's minus 2 points in the final grade. Okay, so I got the point. Okay. Okay, but did you understand the idea? So
yeah, perfect.
The real part tells you whether you are decreasing or increasing. If it were exponential of 2t, it would, if the eigenvalue had a positive real part, okay, this would increase. Otherwise, it decreases. Okay. So you can say something like this. You can say something like this. Oh. Clear everything. Suppose that you have your eigenvalues, one here and one here. That's this complex plane. And you have your time response. This will be something like, it's a sum of two exponentials, two negative exponentials. Now, if you have something which is in the C plane positive exponentials, you will have something which will be, starts here and goes up. Now, if you have something like this, you will have, what does it do? It starts oscillating. And then what happens to the oscillation? Increases or decreases? The real part, this is the real part. Okay, this is the real part. It's negative, so it decreases. It multiplies by the exponential of a negative part, so you are decreasing. If you are here, you start. Okay, you understand the point? What happens if I have my eigenvalues here? So this is time. I think there is a slide with this book. What happens in this situation?
Is the cosine?
It's some oscillation. Does it decrease? Does it increase?
I would say it stays the same because the real part is
It
zero.
stays the same. Okay. Okay. This is in time. Now let's look at this in another way. Let's look at this in another way. So let me use a different color. In state space. So I put here the state space. So x1 and x2. What happens in this case? let's start by, say, this example here. You start here, and what happens? You will have two oscillations, okay? So it will do oscillate, but then the oscillations are decreasing, so you do something like this. X1, X2. Okay. What about here? If you start here, what happens?
Start slow and then it increases.
Bigger and bigger. Okay? Because the oscillation is increasing. What about here? What about here? You are always having a what do you call it? Periodic function. So
Circle?
an ellipse in general
Circumference.
could be a circumference, but in general is a ellipse depending on the scale of the equations.
Okay.
Okay. Now, does it go in this direction or does it go in the other direction as well as the others? Depends on what. We should look at the equations. Okay, for this, but it's a circle for sure. Okay, now one more case, which is an interesting case. Suppose that you have an eigenvalue on the left and an eigenvalue on the right. It's a sum of exponentials. One goes to 0, another goes to infinity. Okay. So let's go directly to the state space. What happens is that there will be directions. I don't know, maybe this one, I don't know. We are going to study this better. Okay. And along, okay, can I clean everything here? Or do you want to make questions? So before looking at this case in which you have a negative eigenvalue and a positive eigenvalue, before this, the other thing was understood. So you have three things. You have the complex plane in which you have the eigenvalues. You have then the complex plane in which you have the eigenvalues, the time response, and the phase portrait. So this would be something like, could be like this, something like this. Okay, depends on the going to 0, and this one goes, I don't know, depends on the combination of those. Okay, so you have these three things. These three things: complex plane, time response, and in red the phase portrait. Any question about this? And by looking at the eigenvalues, you see to have an oscillation, I need complex conjugate eigenvalues. To have a steady oscillation, I need 0 real part of the eigenvalues. If the real part of the eigenvalues is negative, then the oscillation is damping, is dying out. Otherwise, it goes. Okay. So let's clean this. Clean. Now, suppose that you have, let me change my color. Suppose that I have in the C-plane one eigenvalue on the left and one eigenvalue on the right. So this is the real part and this is the imaginary part. Okay. Now, I know that xt is k1. Suppose that this is -1 and this is 1. Okay, and let's give values to the eigenvalues. Suppose that I know that one of the eigenvalues is 1, 1. So, and suppose that this corresponds to the -1, so minus t plus k2, and now 1 minus 1 exponential of t. Okay? And I want to find out the phase portrait. So I now have a plot in which I have here x1 and I have here x2. Okay? And I'm going to mark these eigenvectors. So 1, 1. So 1, 1 is something like this. And 1 minus 1, which is something like this. Okay? Now, suppose that you start aligned with this eigenvalue. Suppose that you start here. Over the direction defined by the eigenvalue. Okay? And this corresponds to this eigenvalue here. Where are you going to? Left, right?
Then down.
Where? José Basílio, you said something, José?
Don't you have to make the spiral down because it has the negative exponential?
Yes, but then you have the other term. Can you say that this other term does not count if you start there? Remember, this K1 and K2 depend on the initial conditions. So how can I find the initial conditions for this situation here? Suppose that this is, say, my initial point is 0, 0.7, 0.7. So they are aligned with this eigenvector, 1, 1. And I get some K1. What can you say about K2? So your x0 is 0.7, 0.7. Okay, so you have 0.7, 0.7 is equal to K1, 1, 1, and then what's the value of this exponential? What time should I consider here?
It's 1.
Times 0, it's 1.
So it's 1, so I don't put anything, plus K2,
Plus K2.
1 minus 1, exponential of 0, so it's 1. Okay, now what can you say about K2? So you have this vector, has the same direction of this vector. Do you need a component from this vector?
So should be
To express the vector in green, do you need some component from this lower vector?
no.
No,
No. So what can you say about K2?
it's 0.
It's 0. So K2 is 0. Okay. You can solve the equations to convince yourself, but to get this vector in green, I just multiply by what? I just multiply this vector. In this case, it's very simple. By what number?
0.7.
0.7. Okay. So if I start aligned with this vector, okay, if I start aligned from this vector, I stay aligned with this vector because K2 is 0, and then I just have this component. Am I going close to 0 or away in this case?
Close to 0.
Why?
The exponential has a
You are
negative.
multiplying by this negative exponential. So here, you go here. Now, what about if you start here? What happens? Aligned with the eigenvector.
Also goes to 0.
You will stay again aligned with the eigenvector. And so it's still this exponential that counts. So you will go. Okay, so all these points you go to 0. What about here? Still aligned from that. Where are you going? Down or up?
Goes up.
Goes up. Okay. So along the if you start along the eigenvalue that multiplies by the negative exponential, you approach the origin. What about here? If I start here, what happens? What happens now to the K's? What can you say about K1 and K2, or at least one of them?
K1 is 0.
K1 is 0. That's right. K1 is 0 because now you don't need any component from this first vector. Okay? And where are you going to? Now you are multiplying the eigenvector by a positive exponential. So
Go away.
you go away. That's very good. If you go away on a summer day, then you might as well take the sun away. Okay. What about here? Also aligned.
Yeah, again.
So again, you go that direction. Okay? Now, suppose that you start here, close to this negative eigenvalue, but not exactly aligned with it. So there is a small component that implies this term. It's small, but it's there. So what happens? You would move in which direction? If you had no component from this one, you would move in this towards 0. But now you have, this is not exactly 0, so this exponential starts to grow, and what happens? Where are you going to? You are more and more deviated in this other direction. So you will go, but now you deviate more. Okay? You see? If you start here, you do something like this. And if you start here, what happens? Now the term in the other direction, corresponding to the positive exponential, the same thing like this, deviates in the other direction. Okay. And here is something like this. Okay, that's why this is called a saddle point, because this looks like principal directions in the saddle. Pontcella. Okay, looks like a saddle, horse saddle. So when you have a negative eigenvalue and a positive eigenvalue, you need to compute the eigenvectors. You need to compute the eigenvectors. And then along the eigenvector that multiplies by a negative exponential, you approach 0. Along the eigenvector that multiplies by the positive exponential, you go away from 0. And any other point is a composition of both of these movements. Okay? So we stop here. And in the next class, we are going to make an exercise in which I will give you 4 state models and 4 phase portraits. And the idea is that you compute the eigenvalues and the eigenvectors and say which is which. Pair the state model with the phase portrait. That's the next exercise. Okay. Then there is another interesting exercise, which is to interpret the Waterloo battle, but that's more advanced. Okay.
Okay.
Any question?
No, thank you.